This video is for AP Calculus BC. This is section 9.4, part B. We're going to look at the limit comparison test. As you can see here, it's not something that's part of the official AP syllabus, at least as of 2016. 2017 it will be. So the limit comparison test is extremely useful. So even though it's not required in 2016, I'm still going to show it to you. I think it'll make life easier for you in certain circumstances. And those circumstances would be when you're looking at a series whose nth term doesn't fit a geometric series, doesn't fit the P series test, so on and so forth. And it's very difficult, maybe even practically speaking impossible, to get a good direct comparison. So in a case like that, we would use the limit comparison test. Here is the limit comparison test right here. If we have two series, both of which have positive terms, then we can calculate this limit. Limit as n goes to infinity of one series over the other series. It doesn't matter which one is which. If we get L, some number, and that number is finite and positive, then the two series both go the same way. They either both converge or both diverge. And so if we know whether, maybe the A sub n or maybe the B sub n, if we know that one of those either converges or diverges, then we could use this then to say that the other one follows suit. It behaves in the same way. So a couple of keys here as far as what to pick in a comparison for the limit comparison test. Pretty simple deal. The function that we pick needs to be of the same magnitude as the series that we are attempting to test. Magnitude would be the relative difference between the degree of the top and the degree of the bottom. So this can be very effective for kind of complicated variations on the P series. And so show you a couple of examples. We'll start with number one. And number one is not really one of those complicated ones. In fact, if you look carefully at number one, you should recognize number one as something that we've already studied. And if right now you're shouting at the computer screen, it's a harmonic series, you are definitely correct. And so I thought I'd show you this one just from the perspective of that harmonic series always diverge, and so this one should diverge. And so I want to show you how this works with the limit comparison test. I'm going to compare it to sigma from 1 to infinity of 1 over n. So the reason why I'm picking 1 over n is it's very simple. Also, I know that 1 over n diverges due to the p-test, or we could even call it a harmonic series as well. But we know for sure the convergence or divergence of 1 over n. And we're pretending like we don't know the convergence or divergence of this one. But again, I just want to show you how this works with something that you already know about, and hopefully that'll give you some trust that all this works. So if you look back, or if you think back to the limit comparison test, it goes like this. Limit as n goes to infinity, and then you simply have to put one nth term over the other nth term. So maybe I do 1 over 2n plus 5 over 1 over n. It could go the other way if we wanted to. I'll just do it this way. This would give us a limit as n goes to infinity. If I do that copy dot flop we've looked at before, we actually end up with n over 2n plus 5. Okay, so we could use L'Hopital's rule here. We could use those old pre-calc tricks. Whatever the case is, we're going to end up with 1/2 for this limit. Now, because that number, what we just calculated, that number 1/2, because that is positive and finite, that means both series do the same thing. And since we know that 1 over n from 1 to infinity diverges, we can say, therefore, sigma from 1 to infinity of 1 over 2n plus 5 also diverges by limit comparison, and we've got it. Okay, so you got to pick a good series to compare with. You got to calculate that limit and get something that is positive and finite. And if you do that, if you're able to come up with that, then you are then able to come up with a conclusion as to whether the series we're looking at converges or diverges. Okay, let's take a look at number 2. Number 2, a little more complicated, not as obvious as number 1. So let's think this through. This is definitely not geometric series, so we can't do that. This is not a p-series, so we can't do the p-test. As far as the integral test, hadn't thought about that. It doesn't look like the denominator factors real nicely, so I don't know that we could really integrate that, at least by the methods that we've learned so far. Direct comparison could get really complicated due to the fact that you've got 3 terms in the denominator. It's going to be challenging to come up with something that's going to work with that direct comparison. And so I'm proposing that it would be best to use limit comparison here. So here's what I'm going to do. I'm going to notice that the top, the degree is 0. And in the denominator, the degree is 2. So that's my magnitude. There needs to be a difference of 2 between the degree of the top and the degree of the bottom. So that opens me up to all kinds of things that I could use. For instance, I could use n over n to the third, or n to the 112th over n to the 114th. I hope you see what I'm getting at, because both of those would, get a cancellation. The better or best comparison would be this one. So I'll write compare to sigma from 1 to infinity of 1 over n squared. That's the exact same magnitude. The degree of the top is 0, the degree of the bottom is 2. And so this should make a good comparison. And we can say that this converges by the p-test because p is equal to 2, which is bigger than 1. Okay, so now we set up our limit. Now that we have something we know, a known series, we can say limit as n goes to infinity, and I'm going to put 1 over n squared over 1 over 3n squared minus 4n plus 5. I think I might have flipped the order here. Doesn't really matter. Let's see what it looks like now. So limit as n goes to infinity, it's going to be 1 over n squared times 3n squared minus 4n plus 5. Okay, so then I can take that and I can, essentially just extend this. And now, whether I use L'Hopital's rule or maybe I would use the pre-calc trick, there's a number of ways to approach this. You can see the degree of the top and the bottom are the same, and so we should get 3 for that limit. And therefore, since that number, 3, is positive and finite, we can say then that, therefore, our original series of 1 over 3n squared minus 4n plus 5 must also converge by limit comparison. Okay, I hope you're getting the hang of this. Definitely suggest, as we move through the next couple of examples, if you feel like you can handle some of these, feel free to pause the video, try it yourself, and check the video when you're done. Okay, so let's take a look at number 3. Number 3, you can see that denominator is pretty complicated. This is definitely not geometric series. There's no variable exponent. P-test is not going to work. Integral test, not going to work either. I take that back. The integral test would work here, but I think limit comparison is going to be faster. Okay, so I got to think of something to compare this to. Notice at the top, the degree is 0, and in the denominator, the degree is 1/2. Okay, so what I'm going to do then is I'm going to compare to sigma from 1 to infinity of 1 over root n. So I've created the same magnitude difference in the degrees there, but I've got something that I know a lot about. I know that this series that I've picked diverges by the p-test. Because p is equal to 1/2, and 1/2 is less than or equal to 1. And so I've got something that I know, and I'm going to compare it by using limits to what I already have. So I'm going to say limit as n goes to infinity of, I'll write it as 1 over root n over 1 over root 3n minus 2. And that's going to give me limit as n goes to infinity of, it's going to end up being root 3n minus 2 over root n. If you think back to some of those old rules that we learned in algebra, we can then say that the quotient of two square roots is equal to the square root of the quotient. So limit as n goes to infinity of square root of 3n minus 2 over n. Now as I apply my infinity, see that I'm going to get root 3. Again, using a L'Hopital rule scenario is fine. You can also use the little trick. There's plenty of ways to handle that. But we're going to end up with root 3. And once again, because that number is finite and positive, we know then that our series will go with the one that we're comparing it to. And our series that we compared is a divergent series. So we can say then, therefore, our original series, which was sigma from 1 to infinity, of 1 over root 3n minus 2, diverges by limit comparison. Okay, so I want to remind you that this is not a required topic. And so because of that, the AP test, at least in 2016, is not going to require you to show all this work. And so I want to finish off these last two by showing you maybe why I think this is such a helpful thing, why I think it's worth teaching even though it's not required. It really comes down to speed. And so I think what you'll be able to do eventually, maybe already you can do this, you can start to look at these and use the magnitude to kind of help you determine whether our series converges or diverges. So let me give you an example. What I'm going to do here with number 4 is not officially using the limit comparison test. It's using that pattern though, and I'm going to basically be able to answer this very, very quickly without doing a whole lot of work. And the reason why I think that that's a valid thing to teach you and to show you here is because all of these things where the limit comparison test will be useful, at least in 2016, will show up in the multiple choice section, and of course you don't have to show your work there. So let me give you a look here at number 4. In number 4, what I would notice is that the degree of the top is 2, the degree of the bottom is 5. And so our magnitude is going to be the same thing as, if the top was 0 and the bottom was 3. There's a difference of 3, right? So if you think back, if there's a difference of 3, we would probably compare that to 1 over n cubed, right? And we know that 1 over n cubed does what? 1 over n cubed diverges, or excuse me, converges. And if we were to go all the way through with the limit comparison test, you know that these two series would go the same way. And so I would immediately look at this and say, because the difference in the degree of the numerator and the denominator is 3, I'm going to say that this series converges. If that difference was less than 1 or equal to 1, I would say that the series would diverge. Take a look at number 5. The top, the degree is 1/2. The bottom, the degree is 2. That's a difference of 3/2, of course, or 1.5. And so I'd say based on that, this series converges. So I'm almost kind of using the p-test rules with these. Again, these last two numbers 4 and 5, I'm not really showing you all the work that would go with the limit comparison test, just trying to show the pattern that you could use to complete problems like this very quickly and hopefully very easily. So I think that's it for the limit comparison test. It is. So we'll be moving on to section 9.5 in the next video.